Hello everybody, I'm Vivek. Welcome to my channel, and today we'll be talking about chemical shift and shielding in continuation with the NMR videos that we have seen earlier. We have seen that dissimilar isotopes require different amount of energy to undergo transition from lower energy spin state to the higher energy spin state. This is because we know the precessional frequency is dependent upon magnetogyric ratio and the applied magnetic field. Now, if the magnetogyric ratio is different, then the precessional frequency would be different. So, let us take the example of proton and carbon 13. Now, we know proton has a mass number of 1, or hydrogen has a mass number of 1, and C13 has a mass number of 13. So, the the magnetogyric ratio is different, and since the magnetogyric ratio is different, the precessional frequency for the proton is 400 megahertz at 9.4 tesla and 100 megahertz at 9.4 tesla. So this indicates they would require different amount of energy to undergo transition from lower energy spin state to the higher energy spin state, because the precessional frequency is different. Now, what about nucleus of the same isotope? Depending upon their molecular environments, they too need different energy to undergo transition from the lower energy spin state to the higher energy spin state. If you remember, we had discussed the use of NMR is to identify different type of magnetic environment present in the molecule. I had taken the example of CH3, CH2, OH and CH3O, CH3. That is, I had taken the example of ethanol and ether. I had mentioned that in case of ethanol, we have three magnetic environments. I had labeled them as A, B, C. However, in case of ether, I had told that there is only one magnetic environment, and we had labeled that as A. So, and I mentioned that since ethanol is a dissimilar atom, we have three magnetic environment, and since ether is symmetrical, we have only one magnetic environment. Now let us understand that why this magnetic environment is different. To understand the difference in the magnetic environment, let us first understand the meaning of this word chemical. When we say chemical, chemical is always associated with electrons. So the term chemical is associated with electrons. As of now, we have seen nucleus is responsible for nuclear magnetic resonance spectroscopy, but along with the nucleus, it is also the electrons associated with that nucleus which play a critical role. Now let us recollect that we have, in case of hydrogen, we have one proton in the nucleus, and we have one electron which is orbiting around nucleus. We know that if we have a charged particle, and if that charged particle moves, it creates a magnetic field. If we have a proton which is moving, that will have a magnetic field of its own. Similarly, if we have a electron, and if it moves, it will have a magnetic field of its own. Now if you notice, the arrow that I made for proton and the arrow that I made for electron is different. You know the reason, that protons are positively charged whereas electrons are negatively charged. So whatever is the magnetic field of proton, electron should have exactly opposite magnetic field. Now we know that when a proton is brought under the influence of a magnetic field, it undergoes precessional motion. So if I say that the magnetic field applied is 100%, now this magnetic field ideally should reach the proton as 100% when the electron is absent. But now we know that the electron is present, and this electron also has a magnetic field which is opposite to that of the proton. So what this electron would do is, this electron would oppose the incoming magnetic field. However, electron has a mass which is extremely negligible. That is the reason the force with which it is opposing will not be the same, and that is the reason in case the opposition, that is by the electron, let us assume is by 5%. So the resultant magnetic field that the proton experiences is equal to 100 minus 5. So it is only 95% the magnetic field which is reaching, and therefore the precessional frequency that is experienced by the protons is actually lesser than what it should have been in the absence of the electron, because your frequency is directly proportional to the applied magnetic. Here the experienced magnetic field is lesser, so the precessional frequency associated with the proton in the presence of electron is lesser. This electron is actually shielding the incoming magnetic field, and that is the reason the concept is called as diamagnetic shielding. With that background, let me take the example of ethanol, where I mentioned that it has three magnetic environments. Now let us understand why do we say that there are three environments in case of ethanol. If you notice, we have oxygen, and this oxygen is highly electronegative, and this electronegative oxygen will have tendency to pull the electrons towards itself. Now when the oxygen is pulling the electron towards itself, let us understand what is happening. As I told you, what these electrons do, these electrons were shielding the incoming magnetic field. Now what oxygen is doing, as it is pulling the electron towards itself from the molecule, it is actually removing the shield, that is, it is de-shielding. So it means now the proton would experience more magnetic field than it would have experienced in the absence of oxygen. By knowing the concept of electronegativity, we know that the ability of the electronegative atom to pull electron goes on decreasing as we move away from the electronegative group. That means the most influenced proton should be the hydroxyl proton, followed by the methylene proton, then followed by the methyl proton. Therefore, we'll have three different magnetic environments in ethanol, that is A, B and C. So this is because of the de-shielding introduced by the oxygen in case of ethanol. That means the most de-shielded would be the hydroxyl proton, followed by the methylene proton, followed by the methyl proton. That means the precessional frequency associated with hydroxyl proton would be higher than the precessional frequency associated with the methyl proton. In case of dimethyl ether, this oxygen would also be de-shielding the methyl proton. And if you notice, the structure is symmetrical. As the structure is symmetrical, the influence of oxygen on both the methyl group is equal. That is the reason we'll just have one magnetic environment in case of dimethyl ether. But yes, this proton would definitely be de-shielded because of the presence of the oxygen. In order to measure the different type of magnetic environment that is present in the proton, we use the term chemical shift. The presence of different magnetic environment in the molecule is measured in terms of chemical shift. We measure the chemical shift by using a standard, and the standard used is tetramethylsilane. Now why do we use tetramethylsilane? If you observe, silicon is not that electronegative, so it doesn't pull the electron towards itself. As it is not pulling the electron towards itself, all the protons of this tetramethylsilane are assumed to be the most shielded among the organic compounds, and since that is most shielded, this will experience the least magnetic field, because the electrons on these protons would be shielding the magnetic field which is coming. So the resultant magnetic field which would be experienced by the protons of tetramethylsilane would be the least, and therefore the precessional frequency associated with this proton would be the least. And let me give that the value as 0. In our example of ethanol, we have three magnetic environments A, B and C. We had discussed that the hydroxyl proton is the most deshielded, followed by the methylene proton, followed by the methyl proton. That means the precessional frequency associated with hydroxyl proton would be maximum, then followed by the methylene and then followed by CH3. At 1.4 Tesla, the precessional frequency of TMS protons is 60 MHz. Then, under the same magnetic environment, the precessional frequency of methyl proton, I am assuming an imaginary value as 62. That of methylene proton, let me assume that as 64. And that of hydroxyl proton, let me assume that as these values are hypothetical imaginary values just for the sake of example. When we apply electromagnetic radiation of 60 megahertz, it is only the TMS protons which would undergo resonance because they are having a precessional frequency of 60 megahertz and it would match, and therefore the energy would be absorbed. What about the others? The others won't undergo any kind of resonance because they have higher precessional frequency. In order for these protons, the other protons to undergo resonance, we need to either change the electromagnetic radiation or we need to change the magnetic field. In case of NMR, what is done is the magnetic field is changed. That is, we go on reducing the magnetic field. So let us say when we reduce the magnetic field to 1.39, this becomes 60 and it undergoes resonance and shows a peak. When we reduce it to 1.38, this becomes 60, undergoes resonance and shows the peak. When we reduce this to 1.35, has a precessional frequency of 60 and it undergoes resonance and shows a peak. That means what we are doing is we are reducing the magnetic field which is applied. That means we are going downfield. Therefore, the chemical shift is defined as the difference between the absorption position of the proton and the absorption position of protons of a reference compound, that is TMS. The unit of measurement of chemical shift is parts per million. We'll discuss that in future videos. Thank you for watching. Please like, share and subscribe. Have a happy learning. Bye.